Super. So, we're a bit early. I can talk a little more. That's good. I can talk a lot. Um, Excellent intro. So we heard a lot about these words, quantum utility. Yeah, this term coined by IBM. Today I'm going to talk about the general problems we're facing in the energy sector and two use cases that we spent the last few years trying to identify. So I think the previous speaker also mentioned that finding the right use cases is kind of one of the hardest parts. And I think the two I'm going to show you today, one is an optimization problem we're solving with the typical QUBO, and the other one is using quantum machine learning. So just to set the stage a little bit, E.ON, for those of you that don't know the company, we provide energy to 47 million customers across all of Europe. We're active in 19 different countries. And what's unique about us is we also manage 1.6 million kilometers of power lines. And what you see here in this plot is the fact that the energy grid is actually alive. So we know that there's renewable integration, but no one really gets this kind of visual. So this is something a colleague of mine made, where you see in Saxony region, you see that as the day passes, we get these yellow, amazing, bright spots, and this is solar energy being generated and injected into the electrical grid. And in this little square, this is a zoomed up local energy grid, which you can see each node, you can imagine being a house, each dot in this graph. And some are yellow, most are red, meaning red needs electricity. And this is kind of what's under the hood of everything that's powering this building even. Lots of interesting challenges come up with this, because the overall picture is this very simple equation, is that the generation of electricity has to equal the consumption of electricity. So traditionally, we see on the left-hand side gas, very sad gas power plants that burn, could be Russian gas, spinning some turbines, making electricity. And on the right-hand side, you see buildings like the one we're in, or houses, or industrial factories. Okay, now this is changing to be decarbonized, thankfully. So we have renewables being integrated here in terms of solar panels and wind farms. And with this comes decentralization. So, we're moving where you had like centralized heartbeats, okay, producing electricity flowing through Europe, where now you have many different little mini hearts producing blood flow to come in everywhere. And the grid was not designed for this, okay? So this is super challenging and introduces the fact that this needs to be digital. The only way to make this happen is if we're digitally tracking, monitoring, supporting all these aspects of a digital grid. And this is a real challenge that we're undergoing right now. So I heard it can take up to 7 years to do the paperwork in Germany to install one power line. So considering we took out nuclear here, now there's lines that don't do anything because there's no nuclear. And so, you really have to make do with what you have in the ecosystem already. This has a bunch of problems. So this is a super complex and dynamic system. And it's diverse with all kinds of different connected assets, generating electricity at different times. And this has to be done in real time to keep the balance between consumption and generation, to keep this equation equal, which this equation being equal is the grid frequency that all of our devices work on. So the department that I come from is a data and AI department at E.ON Digital Technology, and a spin-out from our department has been the quantum computing team. So we started investigating quantum quite a while ago, before the pandemic, that 1 year before the pandemic when things were normal in 2019. And since then, we've partnered with IBM Quantum, and we're also a direct customer with D-Wave for quantum compute access. And we have a team of full-time quantum engineers. We also supervise master's and PhD students through academic partnerships. And basically, we're looking at several different kinds of use cases, and loosely you can break it down into the 3 categories probably most of you have heard before. So, quantum optimization. There's 2 in red here, so V to G is vehicle to grid I'm going to talk about. Peer-to-peer energy trading, community detection about using local renewable energy. And the last one's dynamic pricing, which Flash tomorrow, one of my collaborators and colleagues, David, who's here, will be talking about that third use case tomorrow in the other lecture hall. So if you find this talk interesting, I encourage you to come to our talk tomorrow. We also look at quantum machine learning, generally dealing with anomaly detection about the grid or power plants. And lastly, what a lot of people don't realize is that the electricity that we use is bought on a market. It's called the energy market. And there's different intraday or day-ahead markets. And all this fun stuff that you hear that the banks do about option pricing and things, this can all be applied to this sector, so energy economics. Contract pricing, portfolio optimization, all that stuff is also applicable in the energy sector. So moving to two quantum optimization use cases. This is a nice plot, came from a preprint that we did as part of the IBM Quantum Optimization Working Group, which we're a member of. And basically, you can kind of break it down simply into these four spheres. So on the left-hand side, you have industry-relevant problems that we need to use for our businesses. And inside of there is a circle, probably too big. It should be smaller. It's the hard problems. So what are the problems that are actually difficult? And you only know that by getting into the deep details. That's the best way I can say it. On the right-hand side, you see our quantum world. So you have fault-tolerant quantum computing, which, as the panel was mentioning earlier, it was a really good point that even if you have fault-tolerant quantum computers, it's only as good as the noisy qubits that they're built on top of. So you see noisy quantum computers as a subset of the right-hand side. And what we're interested in at E.ON is the intersection of these 2 points that are industry problems, they're hard problems, and they will work on noisy quantum computers, but of course also fault-tolerant. And we spent years trying to find out stuff in this middle slice with a lot of work. So the first use case is something we've been working on, as I mentioned earlier, with IBM Quantum for the last year and a half, actually, to give you an idea about how much effort this is. And it's involving this concept of vehicle to grid. The underlying topic here is actually called a unit commitment problem. And the unit commitment problem is, let's say you need to create a certain amount of energy in general, so 5 megawatts of energy. What do you use to make that 5 megawatts? Do you take 1 megawatt from a power plant and then 2 megawatts from a wind farm, etc., to sort of add up to 5? Because this is what the customers need. So you can look at this from an electric vehicle perspective. So this is a super interesting topic. This is the future of electric vehicles. So Tesla, for example, piloted a project in California last year, testing this exact principle, which is basically the way we charge EVs now. You can do maybe smart charging, where it charges a bit slowly, using energy market data to just kind of do it as cheaply as possible. But the other direction, that's the 2 part in vehicle to grid, is the way cooler one, which is basically discharge your vehicle and make you some money on your energy contract once the car batteries can handle that. So the idea of this is, why would you be using electricity generated in a power plant in Hamburg right now when there's a bunch of EVs plugged in Berlin right now? Why don't you just discharge each car battery by a tiny slice? Okay, and then that little slice, you add them up, and then you get enough to power this building. And as long as those cars are fully charged when your owners unplug them, then everyone's happy. So you use local energy that was stored in what's known as a virtual power plant, VPP. So in an optimal approach, this is an extremely hard problem. This is an exponential runtime curve where you see that even up to 25 vehicles, to figure out how do I discharge 25 vehicles to meet a unit that I've committed. I've said, okay, I'm going to sell a certain amount of energy at this time of the day, and then the next time of the day I need this different amount of energy. I need to discharge and figure out how to schedule which cars to discharge to meet that demand. And yeah, so realistically, you can simplify it a little bit, and you can get quite better. So you can do basically 1,000 to 2,000 vehicles, I would say, in like 15 minutes. But that's still not enough, of course, for a whole city or a whole country or a state, yeah? So this is a particularly challenging version of the problem, but it's physically realistic. And so what we did with IBM was we wanted to look at, instead of doing the typical cubo that most of us have heard of, let's try to figure out a machine learning heuristic. And what we ended up doing was sort of taking a bit of inspiration from AlphaGo. So the main concept behind AlphaGo and sort of the approach that we took is we used what's known as a Markov decision process. So you basically start with a car, its battery, it's gray, hopefully you can see it, yeah? It's an empty battery, and you say, okay, now at time t, the battery's empty, now I have to decide two things. Do I charge it a little bit, or do I charge it a lot in the next time step, the next minute or so? And now it's kind of like multiverse Marvel stuff here, because you basically have an infinite tree of decisions. At each time slice, you choose to charge or discharge the vehicle, and by how much. And if you brute force this, you can do this for small examples. You brute force it to get to the end, to the far right-hand side, which is the final state in the vehicle, and you see he's very happy, he has a full car battery all charged. But along the way, what path in the universe did he take to get there? And each path obviously has a different monetary value, right? Were you selling energy on the market? Were you buying it cheap on the market, etc.? And so what we did is, for a small set of cars, you can actually compute this brute forcely. That's called approximate dynamic programming. And you learn what the optimization algorithm, the steps it took for each car, for each time step. And then what you can do is you can train a machine learning algorithm. So you can train a multi-class classification model, basically, and you can say, okay, so great, you brute forced it for 10 cars, super, and you figured out a kind of path to say, at each time step, do I charge, discharge, or do nothing? And what we do is take this training data and we train a machine learning model to then be able to scale this to millions of EVs, not just 30 anymore. And so that's what we did. So the quantum part now it comes quantum, is we used quantum kernel methods. So I think this is also familiar to the technical people in the audience. So this is a paper from IBM from several years ago, published in Nature Physics. So it was the first paper demonstrating a rigorous and robust quantum speedup using a quantum machine learning algorithm, which kind of depended on the data set that was being used for. But we used the similar family of quantum kernel here. And not only did we use it, but we ran it on real hardware at the utility scale. So this is a picture of a 100-qubit circuit of depth 50. So that's, for anyone that's used real computers to do anything, that's pretty good. So 100 by 50, that's within error mitigation regime. And in the end, what we ended up getting was a 10,000 runtime improvement in our machine learning heuristic, both classically and quantumly. So I'm not claiming quantum advantage here, but we are claiming that basically if you look at this pink curve, this is this classical brute force, and you can see the runtime scaling beyond or into the regime where we need to be able to solve it quicker. And then you can see basically two straight lines. So QSVC and SVC, the quantum one. So SVC has some overhead because you have to submit it to an actual quantum computer, okay? Ideally, that gets faster in the future. Or maybe with the European data center, there's less over-the-wire transmission for us instead of sending to New York. But that's a promising result. And the accuracy results, we'll have to wait. So we're finishing a paper, and we'll be putting it online in the next month or so. Last use case here involves the concept of peer-to-peer energy trading. So peer-to-peer energy trading is also super interesting. It's just, you have a community of houses, we're all connected to the grid, and some people are lucky enough to have solar on their roof. And that solar is powering their house, and you basically you don't want to do anything. Your energy meter should be able to do it on its own, to automatically sell this electricity to maybe your neighbors. Which neighbor or how far down the road? That's an algorithm that figures that out. And that's basically what this is. So instead of your neighbor, again, buying gas-generated electricity from some power plant somewhere else in Germany or Europe, you leverage your neighbors or your local neighborhood's excess energy, which is even renewable. So this is work done in collaboration with Aquarius GmbH, which is a spin-out from LMU, the University of Munich, which the talk tomorrow will be with Aquarius, as well as University of Oxford, and it's funded by the German federal government. So if you look in a very toy model, you can look at a sort of low voltage network like this. Every dot is a house, and blue means they're producing excess electricity, and red means they need electricity. And what we try to do is basically color code them. Okay, so what is the best way to group these houses into communities? You can do it naively by area code, but it won't give you any kind of optimal answer that way. So in this case, we grouped into six colors, and this basically balances the supply and demand in those local areas. And the thickness of the lines here are actually the real power flow. So using real electrical engineering calculations, which is not what I am, but there's other people in the team that can do that and know how it works. That's basically really a physically realistic setup. And this is a very hard problem. Again, that's a pattern I'm trying to show. So this is the optimal classical runtime of the problem. If you look at number of buildings versus the runtime, it's a log axis. So basically you see 16 buildings takes about 10 seconds to solve this optimally. 18 is about a minute, and then 20, or a little bit more than 20, again, it's over a 15-minute live energy runtime limit that we impose. So again, no chance to do this for the city of Berlin. So what we can do is to actually do some interesting things. We can simplify the problem to look at kind of an approximate version of it. And there we can do more. We can scale now to the hundreds of buildings, and ultimately, eventually to the thousands, but in this simplified form, we get some very interesting results. So what you see here is the number of buildings at the bottom, so 100, 200, 300, 400 buildings. And you see two lines. You see a quantum line and a classical line. The quantum line is real hardware experiments ran on D-Wave, quantum annealer. And classical, this is the best heuristic we could do using taboo search, classical brute force. And this is real experimental results, and you can see the only thing you can take away here is that the lines get closer because the quantum one is flatter. So what we can say here is that for a real business problem, this is some evidence of a quantum scaling advantage. So it actually scales as square root of n, the number of buildings in the example. And so what we hope to see is as the chips get bigger, as the technology gets bigger and better, if you extend this, you extrapolate this plot out, we're hoping to see, these lines will cross, as the many experimental runs have shown us at the low regime. And then, we're expecting for some kind of quantum utility at this spot where the lines cross, and ultimately the quantum one is faster. But for now, classical is winning, but the scaling is definitely an interesting observation. So with that, thank you for your time, and feel free to add me on LinkedIn.